Hello. Yeah, hi. Hello, hello. Coming back. Okay. Hello.
So, hello everyone. We will be starting in 5 minutes. We'll be displaying the attendance form now. Do mark your attendance.
For those of you who have come uh, newly, please give your attendance in this form. Please scan the QR code and give your attendance. Yeah. So, hello everyone. Uh, Myself Harish and my colleague here Anirudh Pai. And today we'll be teaching a session on our session quantifying information, a session on information theory. So the attendance form will be open till uh, for 10 minutes. Please, whoever has come new, please give your attendance. All right. So let's go. So hi, I'm Harish, and today I'll be taking over the session quantifying information, which is an introduction to the wonderful world of information theory. So in this session, we'll be taking these topics, right? So first, we'll have start with the fundamentals of information theory, which is Claude Shannon, who is called the forefather of information theory with his 1948 paper. And then we'll play a small game in order to get an. We'll play a small game to get introduced to the concept of bits. Then we have entropy and Shannon entropy. Then we have the applications of all these concepts, that is Huffman coding and the Shannon communication theorems. Then we'll have a module where we will see how this concept is used in AI. That is KL divergence, Kohlberg-Leibler divergence, token generation, and temperature. And we'll have a conclusion where I'll give you the overview, resources, and we'll take questions. Okay. So section 1, introduction. So yeah, you may mark your attendance here. So before we start everything, let's play a game, right? So I want you guys to guess a number. So I'll be thinking of a number between 1 and 1024. So you should be, so the constraint here is that you should be guessing that number within 10 questions. So how will you do it? Uh, okay, someone said 236. Nice, but no. That's one question already done. So how would you go about solving this question? How would you go about like asking me questions such that you will be able to get the answer to this? I mean, someone already got it, binary search algorithm. But again, so what is that actually? What are we doing there? All right. So express it in binary, one Q for each. Yes. Oh yes, yes, exactly. Yeah. So I guess many people already know this. So what we'll do basically here is that we will ask like how do I say, we will ask whether the number is less than a given number, that is high plus low by 2. So that is basically asking each digit of the number in binary, right? Yes, exactly. Just like Vivek said, assuming low equal to 0, high equal to 12,024 initial, keep updating the guess. Right? So what are we do? What are we doing here? We are asking a question, that is the number less than a given, which is basically what Vivek said. You are guessing the binary digit every time. Here we are checking the most significant binary digit. So we asked a question, yes or no, whether it is below. So if it's below, then we assign 0. If it's above, then we assign 1. So we asked a question. What happens is that we got information about the answer, which is binary information, either that or this. Right? And this narrowed us down our search space by some amount. So basically here it narrowed down by half, but generally in these kind of questions, you will narrow down by some amount, right? And compounding the effects of all the questions, we will later come to a conclusion that yes, this is our number, right? So before we go into information, like the crux of information theory, let's start with a small probability recap for people who are a bit new to probability. Yes. Is this the most optimal? Yes, that is the most optimal. Okay. So probability of event, most probably everyone will know. No, no. Yeah. Probability of an event most probably everyone will know expected favorable outcomes by total outcomes. Probability of two events occurring together that are independent events, you will know that P of A intersection B, that is the event both of them occurring together, equal to P of A into P of B, if both of them are independent. Yeah. Mostly we'll be seeing only independent events. We won't be seeing dependent events in this course. So yeah, so this formula will be valid, and we'll use mostly this formula for many of the formulas, many of the derivations that we'll be doing. Now, expected values. So expected values, this might be a bit new to everyone. So expected value of a quantity, let's say I of x, a function I of x, is basically the sum of all the all the variables times that function, right? And the sum for all x belongs to that probability distribution. That is expected value. So if you have a probability distribution, then for all the discrete values, the sum of this value x into I of x is expected value, right? So yeah. And then logarithms, I think most probably everyone will know. So if we have a power b equal to c, then we can define the log as log base a of c equal to b, right? Everyone understood? You can say that expectation is same as average, but then not always, right? It's expectation of the variable x is average, the mean basically, right? Any more doubts? So I guess many people will know this already. So I guess this is more. So let's start with the fundamentals of information theory. So let's start with the introduction to information theory. Let's just get into it, the humble bit. So overview of information theory is basically that. Let me give you a small overview. It is a field where information from verbal statements is represented mathematically. So basically, the field of information theory deals with how you can certain conditions divide search spaces by a certain number, basically. So what we did in our previous question is that we asked a question that divided our search space into a much more clearer, a much more smaller space that we can search easily. Okay? So that's what we did here. The surprise and information from a yes or no question is studied and quantified. So basically here we have taken a yes or no question, right? So is the number less than a given number, let's say 512? Then we say yes, we have some other thing. No means we have some other. We have another space. So these are yes or no questions. These are studied and quantified. So this is information theory. This is information theory. Again, you also will be studying how the probability of an event corresponds to the information that it will be giving. So if a depending on the probability, how much information will it give? So how do we quantify this information? Right? Oh, once again. Yes. Just a second. How does this definition? Yes. Multiplier. Acha. Acha. I apologize. It isn't x here. I'm so sorry. It's x, p of x into f of x. Sorry. My apologies. F of p of x. P of x. Right? So this is your expected value. I'm terribly sorry. Okay, and they say, okay. So this is your expected value, right? So this definition of the expected value correlate with the sum of each value, yeah, multiplied by probability of occurrence of each value. Yeah. So that's just the mean, right? So x equal to p of x into x. Right? So that's your mean. Let's continue. So how do we quantify this information? The humble bit. So what we're doing here is that we're defining the humble bit. So the bit was not a new term when Shannon was describing it. He used the term for the first time in his paper, a mathematical theory of communication, which is basically the what spawned this whole uh, field, basically. So a mathematical theory of communication is like the Bible of information theory. It's it's what spawned this whole field. A bit is a unit of measurement for information. It can also be called a Shannon, right? So in essence, what we can say is that a bit is how much information you get when you choose an event that divides the search space in half. So for example, if you have a number between zero, let's take the previous example, and you have a number between 0 and 1024, right? So let's say I ask the question, is it less than 512? So if it is less than 512, then uh, then you have given yourself one bit of information. Why? Because when you give one bit, when you have one bit of information, then you are essentially what you're doing is that you're dividing this entire search space into two spaces, that is 0 to 511 and 512 to 1024. Effectively, you're dividing the whole search space into two, right? Right. So how do we mathematically define the information, right? So Shannon proposed these three laws that um, information has to follow. A definition of information has to follow. So let's say we have I of x, right? Our function I of x. So information is additive. So the most important property here is the first one. Information is additive. That is the sum that you get from uh, the sum that you the sum of information from each. The information that you get from two events is the sum of the information you get from each. Basically, you have two events, let's say A and B. So the information that you get from A and B, both of them happening, is the sum of information from each of them. Yeah. That's the first property. Second property here is, if an outcome is more likely, it gives less information. If you think about it, let's take our example 0 to 1024. Then what are let's say we take a very highly likely event, that is 750, right? Less than 750. So what we're doing here is that we're dividing it into two search spaces that are less than 750 and greater than 750, right? So if we know that this statement is true, then we have divided it into search space that is not as efficient as what we did with 512, right? Because this is less likely and this is more likely. So more likely meaning that if we have not done as much removal, as much rejection, as much as we've done with 500, this one 500. So we have got less information. Do you guys understand? Hello. So, and then we also make sure that it should be continuous without sudden jumps. Like it should be a continuous function. So if information of an event is inversely proportional to probability. So do you guys think which function can solve satisfy all these definitions? It is. All clear? What is information? Well, when you are so basically when you are uh, well, I'll start with I'll make a proper definition like than this. Right? Like so. Yeah. So which function satisfies all three conditions? So we have a hint. It breaks products into sums. So now that we've thought about it, let's see. So we have let us formalize our properties of information. So you have information of A and B both happening is information of A plus information of B, information that you get from B. So information that you get from person is information of that you get from two events happening is the same as information that you get from each of the events added up. If an outcome is more likely, it will give less information. So information of an event A is proportional to 1 by product, 1 by the probability of it. Or basically, as information increases, probability decreases. Sorry, as probability decreases, information increases. So let's say what let's use this property. The probability of an event happening is P of A dot P of B, right? The probability of two events happening together is the product of each of the probabilities, right? So if we use this, then we can see that information inverse relation. I mean, it's not exactly inverse relation. You can say that um, it is in if information increases, probability decreases. So basically, that's what I meant by inverse relation here. Again, yeah. So what we have here is information can be written as some logarithm of the probability. Don't you think? Yeah. So we have information is some logarithm base, some random base a p of x, and then we have a minus sign because we want to have this. Right? We have in if an outcome is more likely, it gives less information. So we have a minus. So if an outcome is more likely, it will give less information. Yeah. So now instead of we having a, so basically information can be anything. It can be minus log base a of p of x. but then we are taking 2 because as we know, the most efficient way of dividing a search space is dividing it into 2, as we say. So this is the formula for information that you get from a probability happening. You can also call it the surprise of the probability, surprise of the event happening. Everyone understood? Yeah. So let's go. So exactly, why log 2 and not log or ln? Okay, we explained inverse relation. It's not inverse relation. So it's like, it's basically, if an outcome is more likely, it gives less information. It's not inverse exactly. It is like information of A is proper. If information increases, probability decreases. If information decreases, probability increases. Right? So that's what I meant. I didn't mean inverse exactly, but then if an outcome is more likely, it will give less information. Right. So why log base 2 specifically and not log or ln? So we are basically explaining everything in binary terms, right? We are saying this or that, which is the simplest way. And in the simplest way, if you take it like this, then we can say that log base 2 makes more sense. Other logarithms also work, but then the definitions of all the other quantities that we'll be using will change. Other logarithms will work, but then they won't be called bits. They'll be called, for this one, it will be called maths. Right? And I'll give this as an exercise. Check out for a natural logarithm as well. Right. So let's continue. Let's take a simple example of a distribution and apply this. Right. So let's start with a small example. Find the information content of getting an A. So let's say this is a probability distribution, and we have 5 letters that can randomly occur. So if you have a chance of choosing a letter, then you have 5 letters, each with these probabilities. So the probability of getting an A is 0.125. Probability of getting a no and 0.375, and so on and so forth. So what I'll be doing here is that we want to find the information content of getting an A. So what is the information content? So what is the formula for information content? I of x is basically minus log base 2 of p of x, right? Yes. So let's see. Log base 2 of p of x means p of x is 0.125. 0.125 is 1 by 8. So log base 2 of 1 by 8, which is log base 2 of 8, which is 3. Yes, 3 bits. Yeah. So basically, the information that you're getting from saying getting an A is 3 bits. Right? 3 bits. 3 bits of input. That is with you can say that basically with three yes or no questions, you can get that answer A. You can say. So one information is basically one yes or no question. So if you ask one yes or no question, then you will get the answer. That means it is one bit of information. Right? Next. So let's take an example of find the information content of getting an R, let's say. Yes. So I guess we continue. So yeah, this is the information content, which is 3. So let's say what is I of R? Yeah. So if we take I of R means, let's take log base 2 of 0.1875, which is log base 2 of, yeah, log base 2 of 3 by 16, which is, yes, 4 minus log 3. Right? Everyone seems to have got the answer. So 4 minus log 3 is the answer. Log 3 base 2. So you will have to take 4 minus log 3 base 2 yes or no questions. Uh, at maximum, you need to ask 4 yes or no questions for getting an R. So let's uh let's segue into the next section with a little bit of a game, right? So have you guys ever heard of World? If you're not, let's play. Let's well, once let's play. So we will go with Wordle. So we have, as we can see, we have 6 chances to guess a 5-letter word. Okay. So let's start. Right? So what do you think will be a good opener for this? Yes, money. Okay, let's start with money. Now we have O is O is green and all the others are gray. So we have it has given us some specific information about the secret word. Let's go with audio. Oh, someone said Slade. Interesting. Found. Nice. Oh, nice. So we have B, O are correct. And then you have O, U and D is gray. Oh, audio. Well, now now we can check all the other words which have B and O in the start and uh, have other letters other than M, N, E, Y, U, N, D, A, I. So now because of all these so because of all these guesses, we are getting some information that this letter is not there in the word. This letter is there in the word, but it's in a uh, different space, and this letter is in the correct space. So boxes. Let's go with boxes. Oh, sad. Boxes. So now let's go with the correct answer. Ooh, books is not the correct answer. Nice. Nice. Yes. Booth. Yes, sir. So now we have the answer booth. So what have we done here? Let's take this. So what did we have? What happened in Word? So what did we do here? We gave a guess. Okay. We basically gave our first guess. Yeah, okay. Okay, we basically gave our first guess, money. Now, money, what happened is that we we had our O as green, which meant that it's in the same place and the letter is correct. All the others were gray. So those letters were not there in the word. Again, then we had some other guesses. All the other guesses, they gave us information that this event, that this letter is not there in the word. This letter is there in the word, but it's not in the correct place, and this letter is there in the correct place. So because of that, we got we got to our answer truth. Right? So that's how we will be solving the wordle. So what we're doing is that we are giving a guess. We are getting information about the guess. We are getting information about the secret word by giving that by the information that the guess gives. That is the sequence at which the gray boxes, green boxes, and yellow boxes give. And later we're using that information in order to guess another better guess. Right? So that's what we're doing here. We had a guess and it gave us one of 3 to the power 5, that is 243 possibilities. A little more formalized here is that, let's say for the word slate, we have 243 different possibilities. So out of each of the 243 different possibilities, so if you take one word, for example, booth, then the configuration of, if our secret word is booth, right? So the configuration of slate with respect to booth is that there is no S, there is no L, there is no A, there is a T, and it's in the correct direction. So you'll get a green letter, and there is no E. So basically our configuration will be this one. Where is it? Yes. No, not this one. Mhm. Yeah. So there needs to be. Yes, there we go. Yeah, that's the shortest branches. Yeah, I'll get to that. I'll get to why slate is the best author. So what we have here is that not exactly, you can't say. So we have slate, right? Slate, our configuration is this. So there is a specific configuration of words that this configuration is common with, right? There is no S, there is no L, there is no A, there is no E, and there is a T. There is a T, and it's in the correct place. Again, so what we're doing is that this slate groups everything into groups such that they 243 groups, where each group has a certain set of words that when you give to the word, it will give the same configuration as slate. When are the secret word will give this configuration, the specific configuration. So to optimize and minimize the amount of words used, what will we do? Right? Yeah. So how do we solve this? So every word divides the space by a certain amount. So what we have here is that if you have a word, you have the word dividing into 243 different branches, where each branch has a certain set of words. What we want to do is that we want to make sure that all of the branches are more equally spread, and that we'll have we need less amount of words to find out the answer. So there needs to be less amount of splits, right? So what happens is that when we guess another word, that is our first word, then it will have one of 243 different possibilities again. We want to make sure that this is done in the fastest way. So the words that on average divide the search space the most should be used. And then that leads us to entropy. And no, not the thermodynamics entropy. It has some similarities, but it's not exactly the thermodynamics entropy. So what is entropy? The measure of the average amount of information that you can get out of an event is entropy. So entropy here is, sorry, not entropy here is basically, it will be represented with H. As you know from thermodynamics, it will be represented with H. Okay. It will be represented with H. And it is the average amount of information. Now, average amount of information is basically expected value, right? Expected value of the information function, right? In statistics, this is obtained by using the expected value. Yes. So therefore, the entropy of the word is the expected value of information it will. Again, it's not a it's not what it exactly is in chemistry, but it is something similar. So how do we solve this? So entropy equal to the entropy of event, which is equal to expected value of the information function. Now we know the information function is minus log 2 base p of x. So now the expected value will be minus x minus p of x into log base 2 of p of x. So what is the value of our expected value of any function is the sum of probability of the function and the value of the function for all the values of x, all the values of x in the distribution. So we now have this formula over here, entropy equal to minus log sigma p of x log base to p of x. So as we know, this is our information part. Now we have the expected value, that is p of x into log p of x. Again, the formula of entropy is so and so. If you want, you can write it down. Now let's take an example of how to use it. Find the average information content. So what we can say basically is that entropy is the average information content that a letter can have in this distribution. That also we can say as a definition of entropy. Entropy is basically average information content of any element in the distribution. So let's take this example. So the average information content is entropy basically h of x, which is equal to sigma x p of x log 2 of p of x. And I hope everyone understood what entropy is. Any doubts? Everyone understood, right? Right. So let's start with this. So the entropy basically here is summation of p of x log p of x. Now if you make the summation, let's say 0.125 log base to 0.125 plus 0.375 log base to 0.375, 0.225 log 0.25 plus 0.1875 log base to 0.1875 plus 0.0625 log base to 0.0625. Right? So let's try solving this. This is again, sorry, minus here. I completely forgot the minus. No, entropy is positive. Entropy is positive. I forgot the minus. entropy is positive. So I forgot minus here. Minus P of X log P of X. So as you can see here, this is minus 3. This is 3 into, so minus 3 plus log 3. Now minus 3 minus log base 2 of 3. This is minus 2. This is minus 4. 3. So this is 3 by 16, which is plus log base 2 of 3. Right? No, again, sorry, plus log here again. Here we have 0.0625. So divided by minus 5, minus 4 we have. Right? So we have the sum equals, let me write here. The sum equals minus 3 minus log base 2 of 3 minus plus log base 2 of 3 minus 2 minus 4 plus log 3 base 2 plus minus 4. So as you can see, you can calculate that over here. This is your entropy. So minus 3 minus 6, 14. So 14 plus 2 log 3. So the average entropy here is 14 plus, no, not 14, but this is, what am I done? But my God, I'm so sorry. I completely forgot the weights. Minus 0.375 minus plus minus 0.375 into minus 3 plus log base 2 of 3 plus 0.25 minus 2 plus 0.1875 into 4 minus 4 minus 4 plus log 2 log base 2 of 3 plus 0.0625 into log which is minus 4. Now the calculations will be done in the next slide. So this is your probability distribution. These are your calculations. Right? So if you do the substitute the log values back, you'll have this log value, this log value, this log value. This is your log value. So you'll get around 2.1084 bits per letter. Do you guys understand? Yeah. Yeah. So basically 3 minus 9 by 16 log 2 base 3, which is you're getting around 2.108 bits per letter. So the average information content of the next letter is approximately 2.1084 bits. Apologies for the last time. I forgot to take the probability. It means that every letter has this many bits of information. Every letter needs at least this many bits of information. This many bits of information. Right? So how do we use this for our Wordle example, right? How do we use this for our Wordle example? Let's just try understanding with this example. What does it physically mean? So let's see. So which guess is most appropriate? So what we'll do here is, let's take crane, snake, slate, and pines. Pines. So which case is most appropriate? So what we're doing is that we want to ensure that which guess reduces the possibilities a lot. So uh, which case can help us find the answer more easily. So crane. So if we find crane, then we will have a few possibilities, right? So with snake, our possibilities are A is correct, E is correct. A is correct, E is correct. N is not correct. So let's say N is not correct. N is correct, but it's in the wrong position. So let's put it with this. These two are not there. So you're having this configuration with slate. With slate, you'll have similar configuration, except here the A is not there. This one is there. This one is not there. This one is. You're having this configuration. With pines, you're having I is not there. P is not there. N is there, wrong place. So let's put a circle. E is there, wrong place, circle, not there. So we have this configuration, right? For crane. So the probability of this config. So if the words actually, yeah. Hmm. So let's see. How do you think you can solve this question? Let's see. Let's see the chat, right? How do you think we can solve this question? Sorry. Hmm, most entropy, right? Not least entropy. So uh, the the Abway 6641 asks, so like for word, we analyze. So we'll take the most entropy so that we'll have the least, we use the least words to find the most, to easily find the uncertainty. Yeah. So just give me a sec. Rain, snake, slate, and pines. So if we say the sea, if we get the guess crane, then the probability of having snake is 1 by 3, right? So 1 by 3, 1 by 3, 1 by 3. And the probability of you getting it all 1 by 4 actually, sir. 1 by 4, 1 by 4, 1 by 4. Yeah, more coverage of possible branches. So what do we have here? We have, if it's crane, all correct, then the possibility is 1 by 4. If it's snake, then the possibility of having this configuration A, K, E is 1 by 4. Then the possibility of having slate is, what do you have here? Anyway, what do you guys think? Anyway, let's keep this as an assignment. So again, let's take a break for doubts and rest. Okay. So I'll give around 10 to 15 minutes for this. Well, more entropy means less information, right? Okay. More entropy means less information. Hold on. One second. I'll get back to that. One second. Cosine theta asks, can you explain why more entropy means more information? Well, I'll get back to you. I will. That is an interesting question indeed. Right. So to answer your question, cosine theta, uh, if an unpredictable or a highly random message provides it, because it provides more normal facts, more facts, like it reduces the search space by a lot. That means your entropy is high. So your information, it gives you more information. So to answer your question, that's your that's your doubt explained. Yes, exactly. So to answer Nitin Kamala Hassan's question, take every word and then check number of tries for the shortest part to get to that word. Yes, 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 exactly. That's what we're trying to find here by information. Like we are trying to ensure that uh, some words they will divide it by a lot. Some words they will divide more equal. Some words they will divide in one into like a very big a very big sample space. The other one will get very less. So basically, you're saying that these words. So you want to divide the sample space more evenly. So that's what shortest path means here. Yes. So has everyone marked their attendance for the second part of the session? Okay. Any other doubts, guys? Yes, exactly. So if all of these are discrete probability, but what if it's continuous probability means? Of course, we'll be using integrals. Need not be integral. Yes. Yes. So we shall restart the session after this short break. So now that everyone has marked their attendance, let's go. Let's go to the second section. Section 2, the applications of all these elements and all these concepts and LLMs. Now, yes, LLMs. This is how there is a very small connection to all of these concepts and LLMs. So we'll keep that for the last. Applications where this wonderful branch can be applied. So to recap, what we did is that we defined the information, that is minus log base 2 of the probability of the event, and then we define the entropy, that is the for each possibility, the summation of the probability times the log of probability and then the minus at the end, because information is minus. So where can this wonderful branch be applied? So now that we know the basics, let's see where this wonderful branch can be. How do we communicate effectively, minimizing the amount of information needed to transmit? I'll give you guys a few minutes to answer this question in chat, please. Okay, so we have a doubt here. Yes, natural language processing is also work, but we have a doubt here. How does entropy end up being an integral? Then would it be sums concerning different intervals? Corresponding surprise. Well, that is an integral. In basically, what we're doing here is that instead of using when you have summation and as the intervals get closer and closer together, say instead of using in summation, we just use an integral. So basically, the summation as the intervals tends to very small number, intervals tend to 0, is just an integral. So coming back to the question, how do we communicate effectively, minimizing the amount of information needed to transmit? I'll give you a hint. So in our previous distribution, we had every element had a certain probability of occurring, right? So can we say that that element can be described with that probability, with that amount of bits, right? So let's say we have A, that is 0.125 probability of happening. So we would need to ask at least two yes or no questions to get to A. So to define A, we need to ask at least two yes or no questions to check whether the given element is an A, right? And then this leads us to Huffman encoding, right? So Huffman encoding is an encoding system that is basically rooted in this entire zeros and ones and this binary information, right? So it basically says like how many yes or no questions do you need to get into that A, right? Yes, 3 questions. Oh, sorry, my bad. 3 questions. I'm so sorry. 3 questions. Now coming to Huffman encoding. Huffman encoding is a lossless encoding algorithm, meaning all the information that you have in your data will not be lost. There won't be any loss. There won't be any missing information in your encoding system. So instead of like using very long, very voluminous data, we are bringing it down to a certain compressed data. So it is a compression algorithm. So this is a lossless encoding algorithm where information theory is used to maximize compression and be efficient with communication. Now, in essence, what Huffman encoding basically does is that what we will normally think when we want to encode something. If we want to encode something, then we want the most frequent elements to be to be encoded with shorter codes. So, for example, if E occurs very often, then we want to ensure that that occurs with only one or depend the uh, shortest amount of data that that encodes the letter. So it assigns shorter codes to frequently used characters or tokens and ensures maximum compression. Right. So let's see how it works. Now this is a little bit of a detour into CS territory. These yes. So how does it work basically is that it first counts all the frequencies of all the characters in the text and notes it down on a list. Now, if you know a little bit of DSA, then you can say it's a priority queue, where like because we want the minimum to be first, right? So we want to be easily accessed. So yeah, on a segue. But yeah, it notes down in a list ordered by the frequency of the letter, smallest to largest. So this is very important. This is how we build that. This is the main thing how the encoding algorithm works. So it's ordered by the frequency of the letters, smallest to largest. The smallest two elements are joined into a larger node, and the value of the node is the sum of the frequencies. The process repeats until there is only one node in the list. Later, directions are assigned 0 or 1, and each node has a pathway in a graph. So, for example, let's see how it works by giving an example. So, let's say we have a word that is, let's say we take the word booth itself, right? So, if we take the word booth, then the probability of each of those happening, not both, let's say some 8 bootlegs, right? So bootlegs. So we have B. The probability of B occurring is 1 in 8, which is 0.125. O 0.25 because there are two O's. T, L, E, G, S all 0.125. Okay. 0.125, 0.125, 0.125, 0.125. Right? So basically what we're doing here is that ordered by the frequency of the letters smallest to largest. So this frequency goes down. I hope everyone can see and understand. Right? Yes. Everyone understood, right? Yeah. So now what we'll do here is that the smallest two elements are joined into a larger node, that is B and T. Let's say we have B and T. B and T, gibberish has a lesser probability. So it should have more information. Yes, basically. That's how we make it into gibberish, right? So gibberish has a lesser probability. So it should have more information. Yes. So bootlegs. So B and T are joined into one node with the value of the node is the sum of the frequencies, that is 0.125, 0.125. Yes, exactly. The least used characters are placed further down the path and require longer paths to reach them, and the more frequently used ones are placed at the top, so they're available. Yes, exactly. So that's what we've done here, B and D, B and T. Then again we'll take the lowest possible nodes. So we'll add it here. So BT 0.25. And then we have LNE, which is 0.125, 0.125. So 0.25. Again, same story. 0 E and G 0.25. Then we have E and G, S and O, which is not 0.25. This is it. O, P, T, L, E, G, S. Okay. 8. Check. Yeah. Okay. Yeah. S and O. S and O. S and O, which is 0.375. Again, the probability sum should be 1. Why is it not? S. Okay. GS. Never mind. PTLE GS. Apologies. Yes, eraser. And we have a node O. O with 0.25. Now we'll be combining these two into a node of 0.5. And we'll be combining these two to a node of 0.5. And so on and so forth until you have a tree. Now I'll show you it. I'll show you it as a demonstration. So let's go with this. I hope everybody can see the screen, the Huffman coding algorithm visualization. So let's type the letter bootlegs. Let's type bootlegs and see what the graph gives. Right? Let's see. Let's build the tree. Now, as you can see here, it sorts based on the frequencies. And what we did it as first one, it merged the least amount. It merged the elements with the least amount of frequency together. So it merged this one and this one because these two have the least frequency into a node of frequency 2. Same thing here. It will also do the same thing next. So E and L also will go together. Now O and this node will go together. These two nodes will go together, and these two nodes will go together. So you're having this tree. So what we can do here is that using this, we can assign a direction a certain binary number, that is 0 or 1. So let's say we take left as 0 and right as 1. So what would be the encoding of O and what would be the encoding of T? Yeah. So basically, what we can say is that 8, the encoding for O will be, we're going right 1. So 1, 1. So encoding of O will be 1, 1. The encoding of T will be 0, 0, 1 because you're going left, left, right. So let's go back to our presentation. Let's try to build that same tree for this text, right? So let's take this text. So our frequency table is given right over here. So if we take this frequency table and we write nodes, then it will be T, E, H, underscore Q, and so on and so forth. So what we can do here is match it with the frequencies Q and so on, right? So now what we can do is that we'll try to build a tree. So our tree is like this. So if you want to take, for example, the encoding for U, what we're doing here is that we'll assume left is 0, right is 1. So 0, 1, 1, 1. So our algorithm for U, for our code for U is 0, 0, 0 1, 1, 1. 0, 1, 1. For example, if you want to take underscore, underscore will be 0, 0, 0 because it is the highest. It has a much higher probability of occurring. It has a uh, higher frequency. So what we're saying here is that 0, 0, 0. We are having a shorter code for a code with a higher frequency. So how is information theory used here? The most information a character or token can carry is defined by surprise. This is a fact. So the most information a character or token that is needed to define it or describe it is its surprisal or information. What we surprisal is information over here. Log base 2 of p of x. If I equal to I equal to log base 2 p of I is the minimum information needed to carry the element without information loss, then the minimum average information for each element cannot be less than the entropy, right? Yes. So basically what we can say here is that the expected value, so the minimum average information cannot be less than the expected value, right? Which is entropy, which is true. Huffman encoding approximates close to the entropy limit that Shannon predicted. So the Huffman encoding is one of the earliest, most efficient algorithms to encode information way before even computer science systems developed to that level. So the entropy limit that Shannon predicted is the theoretical maximum at which the theoretical minimum number of bits that can be used without losing information in order to describe an event, right? So Huffman encoding approximates close rate. This is a good and efficient compression algorithm used alongside other algorithms. I hope everyone understood. Yes. So let's continue. So the uses of Huffman coding is zip files. Huffman coding is one stage of the deflate algorithm. So there is an algorithm called deflate where many compression algorithms like zip, gzip, and dng use this algorithm in order to compress data. So Huffman coding is one stage of that algorithm, typically applied after something called as an LZ77 style pattern matching pass. The same thing goes for JPEG images. You compress JPEG images as well. After you lose a lot, after the lossy part, which throws away visual details humans don't notice much. So basically, there will be some parts of an image where even if they are not in the final product, you will be able to understand. It wouldn't matter much. So that is the lossy part. The remaining data is Huffman encoding as a final lossless compression pass. And many other compression algorithms like MP3 and PDF files use Huffman coding as a Huffman derived encoding. So I'm just putting this one theorem here. So Shannon's source coding theorem is basically what we saw earlier. For a collection of n random variables, each with entropy h of x, the minimum number of bits required to describe the information is n of h of x. Now, how this theorem came about is beyond the scope of this course. So I'm just putting this for your information. It's a really interesting read if you want to go about it. So, what do you think is the most information you can pack in a channel? A small introduction to a small topic that we have. The noisy channel coding theorem. So the noisy channel coding theorem is one of the two theorems that was proposed by Shannon in his paper. So which says that for any channel, there will always be noise involved. So if you want to communicate something, for example, from a point A to a point B, then a channel will definitely have at least some noise into it, right? So there will definitely be some noise which will change the data, right? So there will always be some noise in variability and a capacity C. So a capacity is basically how much information it can reliably carry with having error connection codes without any information being lost to chance or to this noise. So if your information transmission rate is below C, that is R, there will always be a code that can communicate information the closest to zero error that you want. So if you have any, oh, yes, correct. So if you have any channel with a channel rate R, if you're transmitting information with the rate R, then you can ensure that you can bring a lossless, you can bring zero loss into this, and there will always be a code that will ensure that. But if it is above C, this rate is above C, then it is impossible to reliably transmit information. Okay? And a small footnote here, the Shannon-Hartley theorem. The maximum capacity of a channel that has a bandwidth B, a signal strength S, and a noise, which is active white Gaussian noise. So active white Gaussian noise means white here mimics the mimics uh, uniform probability distributions. Gaussian is our Gaussian distribution, basically. This distribution over here, our normal distribution. Noise is unwanted data of power. So this is our formula. Now do read upon this. It's also a very interesting read. So Anirudh will take on from here. He'll be taking a brief intro to machine learning and then.
Yeah, Harish, could you stop presenting for me? Present. Yeah, so I hope everybody can see my screen. So my name is Anirudh Pai. Harish talked about information theory and how like bits and all that is connected. And he talked about Wordle, and I think he told a lot about entropy too. So now, all this is done for encoding. However, when you're working in real life, you need to talk about data. And data is sparse, it can be of any format. And usually, the data that we need is in the form of numbers. So, an aspect of how we can like turn these numbers into bits comes under machine learning, and the way to analyze these numbers also falls under machine learning. So now let's look at what machine learning is. So let's say you have something like, let's say you have a function, but the function is not specified. You're given with a set of data points and you're given with something that's y. So y can be termed as the output. And obviously you'll know the input for this given y also. So machine learning, if I want to represent it mathematically, it means I need to find a function f of x using these data points. And these data points over here represent x comma y. All right. And from that, I need to specify what f is. Usually, and in a broad sense, I can say that machine learning is identifying what this function f of x is. Now, f of x is just taken here for simplicity. You can have multiple inputs, like you can have some x comma y comma z as the inputs and some o as the output. So it doesn't matter. It just matters about what we're doing, taking the inputs and outputs and deciphering a function from that. Now, there are three types of machine learning. So the first one is the most general sense, which comes under the other two as well. So we are given a labeled data point, xi being the input, yi being the output. And you want to learn a mapping of xi to yi. Now, such a mapping is called a function or a relation, depends on how it's phrased. So usually it's a function, the same one as in mathematics. So this is how supervised learning occurs. Like you're given a given set of data points, and from this, you try to encode what the function is. And this is an example which is very abstract, predicting house prices from house features. And another one is, uh, let's say we're given like a multiple set of data points, and we want to find like a given structure or something. So maybe we need to plot a graph. Like for example, if you're calculating, if you have a like set where you're plotting the heights of like students in your class, you just have the our labels xi and you'll have its frequencies. So this is an example of unsupervised learning. So I hope these two are clear. So the third one is reinforcement learning. So reinforcement learning is a bit different from the first two, and it occurs in the form of, positive or negative feedback mechanism. So how it occurs is, let's say you have a given stimulus, like take your own human body, for example. So your human body is a wonderful depiction of how reinforcement learning occurs. So you have an external stimulus and you have an environment. And based on that, all your organs and bodily functions happen. So based on your like external agent A and the environment E, the function has a state S, let's say, and based on a given action B done on the state by the agent, under the effects of the environment, your state changes. And from this, you get to find what the action does. And from this, you try depicting what the function actually is. It's a bit complicated. We don't have to go into depth for this. But classically, that's how we describe it. Now, I hope I hope this is clear. Okay. Now let's talk about an example of machine learning. One great example would be linear regression. So what is regression? Well, if we have to talk about it in a brief sense, regression means we're trying to plot a graph for a given set of points, and this comes under supervised learning, the first type, where we have a given label xi comma yi, and we're trying to predict something from that, a function. So let's say we have a graph over here, and these data points are arbitrary, 20, 40, 60, 80, and all that. Just imagine we have a graph, and we had to have a set of points that are sparsed in this way. And as you can see clearly, like let's say you have to plot a function, but you want the function to be simple. And we have these two constraints. So why do we want it to be simple? Obviously, because it'll take lesser computation time, it requires lesser memory, and lesser number of bits, as we know in information theory. So from this, you want to plot a function. So the simplest thing that I can think of is a constant function. But as you can clearly see, neither of these values are constant. So what's the next best thing? A linear function. Like I'm going in the terms of like polynomial, because polynomials are the easiest functions to work with. So hence I'm thinking of a polynomial. So the easiest function over here is a degree 1 polynomial, which is a linear graph. So I can see that I can plot a linear graph, and all of these values fit in and around the linear graph that I'm plotting. And I'm also given with the input and the output value. All I need to do is find a mapping f to this. And here I'm choosing my function f to be a linear map. And also note here one thing, I can choose my function to be anything. And based on these values, I can find a function that satisfies. So what is linear regression? As I told, but mathematically, let's say your input value is x and your output value is y. I can say that some y cap is equal to wx plus b, which is the required line. Okay. However, y minus y cap is not equal to 0. Why? I mean, it need not be equal to 0, because obviously if you have like many data points, it's not true that all the points pass through the line. Some might or might not. So this has some error in this. And let's call that error epsilon. So what is the actual y? The actual y can be written as y is equal to y cap plus epsilon. And what is y cap? Your assumed value of y given the function f, which is the linear map wx plus b. So b is the bias, which means the coefficient of x, and w is the constant, which we can call as the weight of the line. So here are some key points which you need to note. The sole base of assuming a linear function is because of the way the data points are set. Like they're all centered around this line. Now let's say the data points rose up here as well. Then assuming a line would give me an error because these points don't satisfy this line even by a little bit. Your point is not to make it exactly satisfy. You need to minimize this error epsilon tending to 0. That is our main goal. And like I said, the line need not be perfect and even pass through these given points. Now, how is this correlated with machine learning? So this is my initial set of data points, which is called as the training model, training set for the model. And the learning happens based on this present data set. And from this present data set, I get a function f. Now this function f, like let's say you have a set of 1,000 points. And out of these, I extract only 50. From these 50 points, I'll determine a function f. Now again, I take this function f and I apply it on another set of 50 points such that the two sets are completely exhausted. Now, applying this function f, I might get some wrong answers or correct answers based on how well my model is. Now, if it's wrong, my model auto corrects itself based on how wrong it is, on how error, like how much error is there. So that is what happens. So we'll come to that later. So now one question is, how do we calculate W and V? So this is your predictive output value, and this is your error EI, which is like the real value minus the assumed value. So the best case scenario over here is when each error is 0, that all the points lie on the line. However, is that possible? Well, no, it's not possible. So what you need is each error minimizing itself to like a very low value, or it should limit tending to 0. However, we want the value to be at minima, like I said. And also note one more thing. We cannot take the direct sum of the errors. Like if we want like we need a function of these errors to be 0. Let's say some g of e to be 0. but we can't take the direct sum of the errors. Well, the reason being, let's say we have a line and let's say we have points over here. Let's say these points are equidistant from the line. Now this will have a positive error. This will have a negative error. This will have a positive error. This will have a negative error, effectively canceling all the sum of the errors to be zero. But we know that this line is a terrible fit for these points which are lying over here. Like it's absolutely terrible. So what does that mean? Taking the sum of the errors to be zero, we cannot do that. So we need another function g of ei to be zero, and g of ei is not equal to sigma ei. Now, what function of errors do we minimize? Well, apart from the linear function, apart from directly adding the errors, one might think that we can take the modulus of the errors, right? That is true. We can take the modulus of the errors because that way everything is of the same sign, and the error does not, propagate. Now, somebody asking what about like standard deviation? Well, you can take a standard deviation as well, but that will give you no, like, easy method. And technically what we're doing here is taking the square. So that is some form of the standard deviation. So, okay. Another thing which we could do is take the modulus of the errors. But the modulus of the errors will not work because, okay, as we learned in calculus long back, the easiest way to find a minima of a function is by differentiating that function and equating it to zero at its inflection point. Now, for a modulus function, it's not differentiable. And this actually kind of breaks a few rules. And because of that, we do not use the modulus function. Now, we need all the errors to be of the same sign. And the simplest way to do a function of the errors is a polynomial function. So since degree one does not work and modulus also does not work, we'll go to degree two. Why does degree two work? Because when we take squares, what happens is this error evens out and we get it of the same sign. So we take the least squares error. Okay, so somebody's asking, why don't we take the weighted average of the modulus of errors? Well, the same reason again, because of issues with differentiability. And if you differentiate a like linear function, only the point of non-differentiability can be treated as the minima, but that does not give us any good information. So hence we take the second degree polynomial, which is the error square. So we take sigma error square, which is this. So how do we find the values of W and B? And we need to, first of all, we need to minimize this function. So how do we minimize it? We minimize it by differentiating. Now do note, we need to differentiate with respect to a variable. Yi is a constant because it's given to us. Xi is also a constant because it's given to us. Well, somebody's saying that a quadratic fits the data points better than a linear. Well, one could say that a quadratic will fit it, but the intention of the graph was to make everything as close to the line as possible. So a quadratic can also fit it. That is true. But here, for simplicity, we are taking the linear function. So here, like I was saying, yi is a constant and xi is also a constant. So what are the only variables left? W and B. So we have a function j, which is a variable, which is a function of two variables. And both of these are independent, w and b. So how do we minimize this function? We partially differentiate. So when we differentiate with respect to w, we take b to be constant. And when we differentiate with respect to b, we take w to be constant. And then we equate the derivative to zero. So this is differentiating j with respect to w, taking b as constant. And this is differentiating differentiating j with respect to b, taking w as constant. So we equate this to zero. So now what? So we have a summation of n things. We have a summation of n things. So this is one equation. This is also one equation. And we have two variables to find. So we have two equations and two variables. So now we can find w and b on the choice of x and y. Now again, let me explain why least squares is taken. Number one, all errors become positive and are hence easier to deal with. And larger errors can be minimized further because you're squaring the errors, right? For like small errors, let's say you take 0.1 and squaring it, you'll get 0.01. Like 0.1 is actually a very big error. Some might say it's a very small error, but usually your error should be on the margin of 10 power minus 3 for like getting a good approximation. So the function is differentiable. That is one key thing because we find the minima by differentiation. And any even degree would work. So that is true because you need your errors to be of the same sign, positive. But obviously differentiating something like x power 4 would be much tougher than differentiating a square. And we get a unique solution. Why is that? Because differentiation of a quadratic gives you a linear function. And a linear function has only one solution. So that makes things much simpler. So how is this useful in machine learning? Well, now you have these 50 set of data points that your function operated on. And you get some function f that f assume. Now you determine this on another set of 50 points and you check how close or how further it is from your assumed function on the errors. And then you determine another function fb on another set of 50 points and you keep doing this. Now what happens is every time you do an iteration, there's some memory from the previous one retained. So ultimately, f of a to f of b to f of c. Finally, you get some function f of x, which will be much more closer to your actual function than any of these when you operate on multiple training data sets with this. So another important thing about machine learning is, okay, first of all, I hope everything is clear. If not, you can put your doubts in the chat box. So, okay, now an interesting aspect of machine learning is cross entropy. How? We'll look into that. So essentially, what is cross entropy? Well, Harish explained what entropy is. For a classic probability distribution, let's say you have some probability P of X. So for entropy for a given probability distribution P of X, the entropy can be defined as P of Xi log times Q of Xi, negative logarithm, everything. And you summate this over I. So now, what is cross entropy? Well, let me explain from the next slide. Let's say you have a probability distribution P of X, right? Now, for this probability distribution, you don't know what the function, like here I've taken only 3 points, but let's say you have around like 50 points. Let's say you have some dispersed set of data points like this. Now, for this probability distribution, let's say you want to assume a function f. So for this function f, let's say for some given xi, you get some output as some yi cap. So this is the assumed probability with a given function, with like not the given function, with the function that you assume. So your assumed model, because you don't know the actual function, you have to make an assumption like how we did in linear regression, where we assume the function to be a line, but it need not be a line. It could be a quadratic based on your choice. Here we assumed it to be a line. So based on your assumed function, you get a different model, and that will have slightly different probabilities. Now here, obviously, the difference is pretty drastic. Now, since it's very drastic, that means like there'll be some error. But let's say our function was flawed and we got a large error. Okay. So this is a real model, this is our assumed model. So this signifies the cross entropy between two models. Okay. So we want the cross entropy to tend to the actual entropy. That's when we know a model is nearing perfection. So this is a very nice way to gauge whether a model has like good standards or not. Now, obviously, one thing is, okay, it's not obvious, but we'll need it such that the cross entropy should not be equal to the real entropy. And why is that? Well, the main reason is, let's say we change this model a little bit by adding like, let's say 100 extra data points. Now, if this 100 extra data, now if this 100 extra data points is different from what the actual data points of h of p are, then what will happen is h of p will give an error for this 100 data points, and h of p of q will also give an error if they are equal. But you want the like model q such that it's susceptible to change and like any kind of error and noise. So hence we don't want it to be exactly equal, but we want it to be as close as possible. So this is cross entropy. So this is our assumed, this is our real model, and this is our assumed model. So let's say we have this 0.25, 0.5, 0.25, 0.1, 0.4, 0.5. Then the cross entropy h of p of q is defined as this, summating over x. So as you can see, we do this summation and that we get it. We get the average entropy to be 1.7414 bits. And let's say you calculate like h of p. You'll obviously get it to be different from h of q. I hope that's clear. And yes, the thing that we do is in linear regression is the root mean square of all the errors. That's correct. And I hope this is clear. And now, Hari should be giving a small introduction to LLMs and token generation. So I'll stop presenting.
Right. So I'll take it over from here. Right. So let's see a small introduction to LLMs basically. So what are LLMs? LLMs are large language models. Okay. Uh, why do we go for P of X log P of X? I mean, that is also another way of like using cross entropy, but then it is for like you're finding the you're finding the how do I say this? You're finding the difference between the model data from the original data. Here you're saying the original data from the model data. So it's like you're having a different basis, you will say. So for the first one, the basis is your true data. The second one, your basis is your model data. That's the difference. Anyway, large language models or LLMs basically are programs where been trained to mimic human speech and text generation. So those are LLMs basically. So in a nutshell, how they work is that they work on the principle of finding out the next token. So let's say you have a certain sentence and you want to find out what the next possible token is. So LLMs work on the basic principle of trying to predict the next token after a sentence using the softmax probabilities and tuned in parameters that they have been trained previously that assign probabilities to the next possible most probable token that will be chosen. Right? So that's how a large language model works. So if you have a sentence, for example, then the next word will be taken from this list of probabilities, and you'll find out that it is that word next token. It wouldn't be exactly a word. So, for example, if you have key, it need not be exactly a key. It will be a part of a word. It can also be a part of a word. It doesn't always have to be. So this data, this probability data, is taken from training the model over a large amount of human data, and that assigns probabilities to these tokens. So there is an innate data set that assigns that has probabilities, but then as it gets trained again and again, it will, with newer and newer human data, it'll start mimicking human data. So as Anirudh said, we have one error correction method for artificial machine learning programs is not MSC here exactly, the mean squared error or the gradient descent method. But that is not the only error correction method. So the MSC is not the only error finding method in an LLM. There's also the cross entropy. So the cross entropy is a very useful error correction term that signals that how far the model is from the true distribution. So that is your cross entropy. So cross entropy is a metric used for measuring the error between the AI model and expected human text. So our expected human text is P of X, and our AI model has a probability distribution of Q of X. So like mean squared error, it is an error function that is minimized during training in order to ensure the accuracy of the model to human generated text. So as I said, P is the distribution of word probability for human and Q for the AI. So let's take this as an example. So this is a true human distribution where the words error have a so let's say we have a sentence, for example, and then the next word has from human data is this. So the probability distribution of the next word from the human data is you have a 14% chance of error, 65.2% chance of the 10.2% of hello, and 10.6% of like. Now the AI, after training a lot, it gets this probabilities. So this set of probabilities for the same sentence. There are two AIs that have been trained differently, so that one AI gets this probability distribution, another AI gets this probability distribution. So let's try to find out the cross entropy for each of the models. So this is our human model. This is AI1 and this is AI2. So the calculations are given below. So as we said, the formula for our cross entropy is h of pq equal to, one second. For all the data point, for all the events, all the words in the distribution, h of pq is the summation of p of x log base 2 of q of x for all the words x in the distribution, right? So calculation for model 1. Now if you do the calculation for the model 1, that is the word error, the, hello, and like, then you will get to somewhere around 1.479 bits of difference. So basically what we're saying is that the extra amount of information required to describe Q as 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 an encoding system with P. So basically you have P as an encoding system. So the extra amount of surprise that the AI gets is HPQ. This is 1.479 bits. That is the difference between the AI model and the normal model. Now for model 2, we have using the human data, we do the same thing. So you have the probabilities times the logarithm, say logarithm base 2 of the probabilities of the AI model. So when we do that for the second model, we get a difference of 1.497 bits. So here it's more, it's tiny bit more, but it's not that much more, right? So we want to make sure that the function is most minimum. So which model do you think is the closest to mimicking human data? Yes, that's right. The first model is closest to human data. The second model is a little bit farther away, not that farther away, but a little farther away. So basically, as you can see here, the differences between both the models are very great. So there is almost a 0.05 difference in the probability for error 2. Same here, 0.05 difference. But again, the other two are same. So again, even with this large 5% difference, the number of bits difference is not that much, right? So uses of cross entropy are loss functions for LLMs. As Anirudh mentioned, this is a very prominent function used for the loss function of LLMs to train the LLM into mimicking human data. Next word, prediction. Tokens are assigned probabilities. Cross entropy penalizes the model if it's wrong. So if you have a certain sentence and you have and the model thinks that there is a word that comes in afterwards, then if the word is wrong, then using cross entropy, we can kind of penalize the model and we can make sure that it turns back to normal. And then it becomes more and more accurate to human data. Perplexity. Now, perplexity is a small metric that we use for LLMs to ensure correctness. Now, perplexity is just 2 power h of PQ, right? So perplexity as a metric is just 2 power the cross entropy between P and Q. Now, some other non-AI related uses for cross entropy. You have optimal versus suboptimal coding. So remember that I told you about Huffman coding, right? So there will be some other encoding mechanisms that may not be as good as the optimal encoding. So what you want to do is that you want to find the difference between cross entropy. So the optimal size is entropy, as I said, but the uses, but not every algorithm can go as much as entropy. There is a certain limit that you can go. So when you create this, if you want to find the difference, you have to use cross entropy. Again, an extension of this is like the cross entropy penalty. So basically, what it says is that this message is this encoding system is this much less accurate than the optimal encoding system. It tells you the average length of the message using a suboptimal scheme Q, right? So if you have a true scheme P, and you have a suboptimal scheme Q, then the cross entropy is basically average length of the message using a suboptimal using the scheme Q. Now, a small footnote of addition to cross entropy, we have KL divergence or the Kullback-Leibler divergence. I hope everyone understood cross entropy. Yes. So, KL divergence is also another metric used for the error correction mechanisms of AI. But first, let's give a small intro. So, Kullback-Leibler divergence is basically the quantified difference between the true distribution and another distribution. So, when you have two distributions, let's say this and let's say this, the difference between these two, like not exact per se difference, but then like it's a metric of difference, another metric of difference between two probability distributions, P of X and Q of X. Now the formula for KL divergence is given below. So DKL, so the KL divergence is denoted as divergence KL P parallel of Q equal to the say almost similar to cross entropy, except instead of Q of X, you have P of X by Q of X. Right? So your formula is summation for all x in the distribution. P of X log P of X by Q of X. So you have one probability distribution P of X, one probability distribution Q of X. So P of X, so the KL divergence between both of the probability distributions is P of X log P of X by Q of X, summation for all x. You guys understand? So yeah, looking at the formula, you guys might realize that there is a very important relation between cross entropy and KL divergence, which you can think about. So I'll give you a few minutes, just think about it. So K Palam says, so yeah, yes, basically. Yes. So Apki Param says, so KL divergence is basically true entropy, sorry, basically difference between true entropy and cross entropy, right? Well, I'll come to that. I'll come to that. So if you got that the cross entropy equal to entropy, true entropy plus the KL divergence, you are absolutely right. So cross entropy equals to entropy plus difference between entropy. So to answer the question, yes. So KL divergence is basically the difference between true entropy and cross entropy. So the role of KL divergence. So in LLM models, KL divergence is used to be the safety rates. So for example, so there might be a chance that an LLM model, in order to in order to be close to as human readable text, what it can do is that it will it might take some cheating mechanisms. It might cheat its way and use some other improper probability distribution q of x, q dash of x, that may be very different from our original uh, our human probability distribution. So what this KL divergence does is that it it ensures that these kind of issues do not happen, and it shows how off your model is from the actual data. So basically, you can say it as a safety rates. Okay? Yes. So everyone understood this part? Yes. So yes. So for two distributions, you can say that the KL divergence is said to be the surprise that you get. So the more information you have, more information that you get when you describe one distribution with the information matrix of the other. So let's take the same example, right? So how do we find the KL divergence? Let's see. Let's see how we find the KL divergence. So the formula for KL divergence is DKL or P of Q model equal to sigma x P of x log base to P of x by Q of x. Right? So everyone understood this part at least? So let's go to the calculation in the other side. So as we said, this is our formula over here. So calculation for model 1, when we substitute in the log values, you will get a certain value of 0.008 bits. That is the difference from the true entropy. The difference of the model from the true entropy. That is 0.008. For the model 2, we have 0.0180. So as you can see, for the model 2, for model 2, the difference metric is basically almost 2 orders of magnitude greater than the difference for the model 1. So basically, as you can see, the model 1 is much closer to human data than model 2. So as you can see here, it is 0.0008. Oh no, 0.0008. Okay, so almost 3 degrees of magnitude is lower than 0.0180. Model 1 loses less information relative to the human data. So, and is therefore the superior model representation, as you can see, right? So that's our calculation for KL divergence. So some limitations of KL divergence. As you may have noticed, DKL of PQ not equal to DKL of Q and P. Now, as you can see, this is a very important problem that many people, then that KL divergence has. It is an asymmetric divergence. It is not a true distance metric. It is an asymmetric. So as you can see, cross entropy also is not equal. Same way, there is asymmetry in Kullback-Leibler divergences. So for example, there may also be another distribution where if for example, Q of x is assigned 0. So for any word, if we know that the word cannot come out after this word, like for example, we can't say the right? So we can say that the probability of the token A coming up after the word the is basically 0. So when you use this token, when you use this distribution, the computation breaks, because as you can see in the formula, Q of x should not be equal to 0, right? No matter what, Q of x should not be equal to 0. P of x need not be 0. Q of x should not equal to 0. So here, but it says that Q of x equal to 0. So the computation breaks. So you cannot find the Kullback-Leibler divergence, right? So that is one issue that the metric has. So yeah, thank you. That concludes this wonderful session. I hope you had fun I hope you had fun learning about this new topic. Uh, if you have any doubts or questions, please let us know in the chat. Thank you.